grain refinement. So let us say we are observing the two microstructures. One microstructure is having coarse grain. Coarse grain means number of grain boundaries are few in number. And another microstructure is fine means number of grain boundaries are more. There are more grains in it in the same area. There are more grain boundaries in the same area. That microstructure is called fine grain structure. Coarse grain structure means grain boundaries are only few. As we discussed that, what is the meaning of grain boundaries? Atoms on one side are oriented in one fashion, and on the other side, atoms are oriented in a different direction. And there is an orientation mismatch. Theta is the orientation mismatch, and these regions of orientation mismatch are called grain boundaries. Alright, so these dislocations will be present within the grain, and when we are applying the load on the material, dislocations are moving, and as soon as it reaches the grain boundary, atoms on the other side are oriented in a different fashion. So the dislocation has to change its course. So grain boundaries are obstacles in the movement of dislocation. To cross it, slightly larger stresses are required. Why? Because as soon as the dislocation reaches the grain boundary, slightly higher stresses are required to change the course. So when you have a fine grain structure, before the dislocation comes out, it has to pass through many grain boundaries. So more obstacles, hence more strength. So finer is the grain structure, better will be the strength of material. But remember that grain boundaries means bond length will be larger. And larger the bond length, easily bond can break. And atmospheric oxygen will quickly react over those atoms. So finer is the grain, lesser will be the corrosion resistance. But finer is the grain, better will be the strength. But how to change the grain size, that we will learn in TTT diagram. Based on TTT diagram, you will come to know how we can change the coarseness and fineness of any grain structure. So, in summary, there are three different ways to increase the strength of any material: grain refinement, alloying, and work hardening. Based on the dislocation theory, we can also understand a very, very important principle which appears in low carbon steels. In low carbon steel, we see a phenomenon called yield point phenomenon. In low carbon steels, there is a phenomenon called yield point phenomenon. Yield point phenomena. What is exactly yield point phenomena? If you see the stress-strain curve of any material, it will be like this. Alright, this is the stress-strain curve of low carbon steel. It's a unique curve. So this is called upper yield point. This is called lower yield point, and this is called yield point phenomena or stretcher strains. Stretcher strains or Lucas band formation in this region. Primarily, popularly, it is known as yield point phenomena. Now, suddenly, question comes to our mind that why yield point phenomena appears in low carbon steels? Why yield point phenomena appears in low carbon steels? So we can understand it with the help of dislocation theory. Let us say this is the material and this is the dislocation site. Alright. And as we know that carbon and nitrogen are interstitial impurities in iron. Carbon and nitrogen are interstitial impurities in iron. So let us say carbon is present here at some interstitial site in iron. But the interstitial void is much smaller than the size of carbon atom. Interstitial void is much smaller than the size of carbon atom. So suppose carbon or nitrogen is present at some interstitial site, iron is pushing from all the side. So carbon is very much uncomfortable because all the iron atoms from all the sides are pushing carbon. So carbon is very uncomfortable. So carbon thinks, is there any suitable place for me where I can be comfortable? So carbon finds that there is a dislocation site where interstitial void is slightly larger in size. Is it not? Because there is an extra half plane, so interstitial void will be slightly larger in size. So carbon says, let us go there and sit comfortably. So carbon jumps through the interstitial void and gets accumulated at the dislocation site. Because the H dislocation, as we discussed, that there will be a line. Suppose one atom is on this wall, another atom is on the other wall, and there is a whole plane. And all along this line there will be interstitial void, which is larger in size along the line. So many carbon atom can fit in on the H dislocation site. Many carbon atom, producing a carbon or nitrogen rich atmosphere called quaternary atmosphere. This carbon or nitrogen rich atmosphere is called quaternary atmosphere. So although carbon is comfortable, but still size of this interstitial void is slightly smaller than the size of carbon atom. Carbon is comparatively comfortable as compared to this position, but still the interstitial void is slightly smaller in size. So what happens? The diffusion of this carbon atom produces a strain field at the dislocation site due to the presence of quaternary atmosphere, presence of carbon or nitrogen rich atmosphere. So now what happens? When you apply load on the material, slightly larger stresses are required to break this atmosphere, quaternary atmosphere, because it's a strain field. Slightly larger stresses are required to break this quaternary atmosphere and jump the dislocation to the new site. That is why upper yield point appears in the material. But once the dislocation jumps to the new site, there is no quaternary atmosphere because all the carbon nitrogen is packed here. At the dislocation site is nothing. So slightly lower stresses will be sufficient to keep the dislocation moving. That is why lower yield point and the yield point phenomena appears in the material. Because you have already stressed the material slightly higher value. But to keep the dislocation moving, you require lower stresses. That's why lower yield point and yield point phenomena appears in the material. This yield point phenomena is a problem in processing any material. Because when you process it, generally the material will fracture. You cannot deform it. So, as far as processing is concerned, the yield point phenomena is a problem. Okay? But suppose the yield point phenomena is already over, you unload the material, and when you reload it, yield point phenomena will not appear in the material. Why? Because carbon is somewhere else and dislocation is somewhere else. Okay? But if you wait for some time, this some time depends upon percentage of carbon or nitrogen. This period is around 2 years or so. 1 to 2 years. Depending upon the percentage of carbon. If you wait for some time, then the yield point phenomena will reappear in the material. Why? Because carbon was somewhere else, dislocation went from that place. Now carbon again started thinking, array, from here dislocation went? Oh, dislocation went there. So let us again go and settle that position. So carbon again jumps from this side and settles down at the new location. And due to appearance of again continental atmosphere, there is a reappearance of yield point phenomena. This time period after which yield point phenomena reappears in the material is called strain aging time. Is called strain aging time. So in the manufacturing industries, what is done? There is a skin rolling. We are deforming the material to ensure that yield point phenomena is over, and then we are printing a date on the material. What is the date? Strain aging time. That the industry which I am supplying should consume the material within this time period. Otherwise, as a supplier, we are not responsible for the material. Because as a supplier, I know that the yield point phenomena is going to reappear. So the company has to consume the material within the strain aging time. This yield point, as the percentage of carbon increases, let us say from low carbon steel to medium and high carbon steel, you will not find yield point phenomena. The reason is, when the percentage of carbon is higher in medium and high carbon steel, carbon is not only present at the dislocation site, but at the other interstitial sites as well. So once the dislocation jumps to new position, carbon is already there. So there is no question of appearance of lower yield point and yield point phenomena. So this phenomena appears only in low carbon steels. So we can see that both strengthening mechanism and yield point phenomena, this dislocation theory plays a very important role in understanding the behavior of any material. So in this lecture we learned what are the different ways to increase the strength of material and what is yield point phenomena in low carbon steel. Thank you very much.